Next, I'd like to demonstrate what happens, such as with a pond of water, where we see something on the bottom of the pond, and that appears to be raised up so that the pond doesn't appear to be as deep as it really is. What happens is we might have an object on the bottom of the pond. It might be a rock or a penny. It could be anything. And that rock, if that's what it is, appears to be up here because of refraction. Light comes up, bends away from the normal line. Light comes up, bends away from the normal line. These two beams of light appear to be coming from this point here as if this were an image of this object. So the object appears to be raised up considerably depending upon how much speed change takes place or how much refraction takes place at the surface. To demonstrate that, I'd like to again refer to our Blackboard optics system here. And to do that, I'm going to turn the lights down for better contrast. So here I have the Blackboard optics set up, and I have these beams of light crossing, and I'm going to simulate an object as if the actual object were right there at that point where those beams cross. So I'm going to put that object as if it were at the bottom of the pond. Now I'm going to turn the plastic sideways like this, so the bottom of the pond is going to be here, the top of the pond will be over here, and I'm going to set that object right at the back surface, which would be our simulated bottom of the pond. So I put that object right there, and we see the light beams. The one that goes upward refracts upward, the one that goes downward refracts even more so downward, as if those two light beams appeared to be coming at some point that would make the apparent thickness of this piece of plastic be less than it actually is. Next, what I'd like to do is to demonstrate that on the overhead projector. So now I have here the block of plastic that we've used earlier, and I'm going to lay that block of plastic on top of this transparency here and show that what this lens system sees as it sees an object, the transparency, as if it were raised up. Because what that's going to do is going to change the apparent depth of this actual transparency as the lens system looks through this block of plastic and tries to project that image onto the screen. The distance between the lens and the transparency is critical for a sharp focus. So when I put this on top of the transparency here, we see that it blurs the image. To bring that back into focus again, I've got to raise that up a considerable distance, and then that projection system can again form a sharp image on the screen. And we see that we raise that up quite a distance, almost a third the thickness of the block of plastic in this case. So the apparent depth is about 2/3 the real thickness of the block of plastic. Now when I remove that block of plastic, we'll see how blurry that is. So this shows that the apparent depth is less than the true depth when the light comes up through a block of plastic or from the bottom of a pond up to the top of a pond. Another way to demonstrate that would be with a coin. Here I have a coin here, which is out of focus because it's the same level as the transparency here. I can bring that into focus by bringing it up to a closer position, or I can change the. Let me try that again. I can take it from here and raise it up and bring it into focus, or I can bring the image up by changing the apparent depth by putting this block of plastic on top of it and refocusing it in that fashion. Apparent depth changed because of refraction.